Reality warps in the deep cosmos where common sense breaks down. We are about to journey through 25 astonishing truths about space and time that will reshape your understanding of the universe. You will discover why time is not absolute, how most of the cosmos is invisible, and whether the universe has a true edge. These revelations promise to dismantle everything you thought you knew about the fabric of existence. What single cosmic mystery has always captivated your imagination? Your phone's navigation knows a secret about the universe that you experience every single day. The global positioning system relies on a network of satellites, each carrying an incredibly precise atomic clock. Yet, if we left those clocks to their own devices, they would slowly but surely fall out of sync with the clocks on the ground. They do not tick at the same rate. This is not a mechanical error. It is a fundamental truth of reality called time dilation, a direct prediction from Einstein's theory of relativity. The theory tells us that time is not a universal metronome ticking at the same beat for everyone. Instead, its flow is warped by two things: speed and gravity. Those satellites are high above the Earth in a weaker gravitational field, which makes their clocks run faster by about 38 millionths of a second per day. At the same time, they are moving at tremendous speeds relative to us, which has the opposite effect, slowing their clocks down by about 7 millionths of a second. The gravity effect wins, so engineers must pre-program the satellite clocks to tick slower before launch, correcting for the fact that time itself runs faster up there. Without this daily correction, your GPS would be inaccurate by several miles within just a few minutes. This means the very tool you use to find a coffee shop is proof that time is flexible. To make this even more personal, consider the famous twin paradox. Imagine one twin stays on Earth while the other travels on a spaceship at a significant fraction of the speed of light. From the Earth twin's perspective, the clock on the speeding spaceship appears to tick agonizingly slow. When the traveling twin finally returns home, only a few years might have passed for them, but decades could have gone by for the sibling who remained behind. One would be young, the other old. This is not science fiction, it is the rigorous prediction of our best physical theories. Your own life is a collection of moments flowing at a rate that is unique to your path through the cosmos, a personal rhythm dictated by your speed and the gravity you feel. This fluidity of time forces us to rethink our most basic assumptions about reality, including where we are. We often picture the Big Bang as a titanic explosion from a single point in space, flinging galaxies outward into a void. But this mental image is fundamentally wrong. The universe does not have a center, and the Big Bang did not happen somewhere. It happened everywhere all at once. A better way to visualize this is to think of the entire universe as the surface of a balloon. As you inflate it, every dot on that surface moves away from every other dot. Which dot is the center of the expansion? None of them. The center is not on the surface at all. It is inside the balloon, a dimension that the surface itself does not contain. In our universe, every galaxy sees all the other galaxies rushing away, and from its own perspective, it appears to be the still center of the cosmic motion. We are not receding from a central point like debris from an explosion. We are all receding from each other as the very fabric of space stretches. This means you are, right now, at the center of your observable universe. So is a being in a galaxy a billion light-years away. There is no privileged location, no grand central station for the cosmos. Our home is not a special place in the grand scheme, but merely one point in an infinite, expanding tapestry where every thread sees itself as the focal point. This lack of a cosmic center is humbling, but the universe has far more violent disruptions in store. If you were to fall toward a black hole, the very concept of a stable self would be torn apart. The gravitational pull at your feet would be catastrophically stronger than the pull at your head. This difference in force, known as a tidal force, would begin to stretch your body lengthwise, pulling you into a long, thin shape. At the same time, the immense pressure would compress you from the sides, squeezing you inward. This grotesque process has a fittingly bizarre name: spaghettification. You would be transformed into a stream of atoms, a human noodle spiraling into the abyss. Your own experience of this fate, however, would be just as strange as the fate itself. From your perspective during the fall, this stretching might be the last thing you notice before crossing the point of no return, the event horizon. But for an outside observer watching you fall, the view would be utterly different. They would never actually see you cross the event horizon. As you got closer to that invisible boundary, the light coming from you would be stretched to longer and longer wavelengths, making you appear increasingly red. Your image would also seem to slow down, freezing in time and fading to nothingness as the last photons struggled to escape the immense gravity. You would appear to hover on the edge for all eternity, a ghostly afterimage painted on the fabric of spacetime. This disconnect is not an illusion. It is a direct result of time being warped to an absolute standstill at the event horizon from an outside point of view. The black hole does not just tear matter apart, it shatters our most fundamental expectations of what happens and when. The ghostly image of an object frozen at a black hole's edge is a profound testament to how little of reality we actually perceive. Our senses and our finest telescopes are tuned to only a narrow sliver of what truly exists. The stars, galaxies, and planets we marvel at, the very stuff of you and me, constitute less than 5% of the universe. The rest is an invisible empire ruled by two enigmatic forces we call dark matter and dark energy. We know dark matter is there because we can see what its powerful gravity does. Look at a spinning galaxy. The stars on the outer edges are whipping around so fast that the galaxy's visible mass, all its stars and gas, is not nearly enough gravity to hold them in place. By all rights, these stars should be flung off into the void, yet they are not. It is as if the galaxy is embedded within a vast, massive sphere of something we cannot see, a cosmic glue holding everything together. This unseen dark matter forms a hidden scaffolding, a gravitational skeleton upon which the entire visible universe is built. Then there is dark energy, an even more baffling phenomenon. We have known for a century that the universe is expanding, but the shocking discovery at the turn of the millennium was that this expansion is not slowing down. It is speeding up. Something is actively pushing space itself apart, stretching the cosmic fabric against the relentless pull of gravity. This repulsive force, dark energy, makes up the bulk of the universe's energy budget and dictates its ultimate fate. We are left with a cosmos where the familiar world of atoms is a mere afterthought, a sprinkling of visible dust adrift in a sea of invisible, dynamic entities whose true nature remains one of science's greatest puzzles. This cosmic sea of dark matter and energy is not a smooth, uniform soup. Its structure is lumpy, woven with immense filaments of galaxies separated by staggering, almost empty voids. One of the most terrifyingly empty places we know is the Boötes void. Picture a spherical region of space so vast it could contain thousands of galaxies like our own. Yet within this colossal emptiness, this cosmic desert nearly 330 million light-years across, we have found only a handful of isolated island galaxies. If our Milky Way were at the center of the Boötes void, our night sky would be profoundly, unnervingly black. We would not have known other galaxies existed until the invention of powerful modern telescopes. The existence of such a void defies our early expectations of how matter should be distributed. The universe, on its largest scales, should look roughly the same everywhere, a principle called the cosmological principle. Finding a hole this big is like discovering a single, perfectly spherical ocean trench deeper than Mount Everest is tall, in an otherwise shallow sea. It forces us to ask what processes in the early universe could have scoured matter out so efficiently, leaving behind a near-perfect vacuum on a scale that is difficult to comprehend. This leads to a humbling thought. What if we are not in a special, galaxy-rich neighborhood? What if the Milky Way itself resides in a local void, a smaller bubble of relative emptiness? From our perspective, the universe looks full of galaxies, but that might just be the view from our particular street. We could be living in a cosmic suburb, looking out at the bright, dense cities of galaxy clusters in the distance and mistaking them for the average. This uneven, frothy structure tells us that the cosmos is not a uniform expanse, but a dynamic tapestry of immense clusters and profound voids, a landscape of breathtaking extremes. The uneven cosmic tapestry, woven with vast voids and dense clusters, is not a static sculpture. It is a dynamic fabric that can ripple and wave. In 2015, a century after Einstein first predicted their existence, scientists witnessed the fabric of spacetime itself shudder. They detected gravitational waves, ripples moving at the speed of light, generated by a collision of two black holes over 1 billion light-years away. The event was so violent, so energetic, that it shook the very foundation of the universe, sending out tremors that traveled for eons before finally reaching us. To understand what a gravitational wave is, picture the cosmos as a still, elastic sheet. Now, drop something immensely heavy onto it, like two black holes spiraling into each other. The impact sends waves spreading outward, not through the sheet but of the sheet itself. As these waves pass through everything in their path, they literally distort space. They stretch it in one direction while simultaneously squeezing it in the perpendicular direction. If you were floating in space as one passed by, you would be stretched and squeezed ever so slightly along with the space you occupy. The detection of this subtle shudder was a monumental achievement. The Laser Interferometer Gravitational Wave Observatory, or LIGO, uses two long, perpendicular arms, each 4 kilometers long. A laser beam is split and sent down each arm, bouncing off mirrors to recombine. Under normal conditions, the light waves cancel each other out, but when a gravitational wave passes through, it minutely changes the length of the arms, one stretching while the other compresses. This tiny change, thousands of times smaller than the nucleus of an atom, disrupts the laser light, creating a detectable signal. That first faint chirp, the sound of two black holes merging, marked the dawn of an entirely new way of seeing the cosmos. We are no longer limited to observing light. Now we can listen to the universe's deepest, most powerful vibrations, hearing the echoes of cosmic collisions that are completely invisible to any telescope. That faint shudder in spacetime is an echo from a distant past, just like the starlight painting our night sky. Every time you gaze upward, you are not seeing the universe as it is, but as it was. The light from those stars is a cosmic messenger, and its journey to your eyes takes years, centuries, even millennia. That brilliant point of light we call the North Star Polaris is not a mere 430 light-years away. When you look at it, the photons striking your retina began their voyage around the time the Roman Empire was at its peak. You are witnessing a historical event, a snapshot of that star from an era of gladiators and emperors only now arriving at Earth. This is not a philosophical metaphor, it is a physical reality. The star you see tonight might not even exist anymore, having met its dramatic end in a supernova explosion long ago, its final light still traveling across the gulf of space. This principle transforms our most powerful telescopes into genuine time machines. When astronomers point the Hubble or James Webb Space Telescope at a faint smudge of light a billion light-years away, they are not just studying a distant galaxy. They are peering back through a billion years of cosmic history, observing that galaxy as it was when life on Earth was still single-celled organisms swimming in a primordial ocean. We are watching the universe's own childhood, seeing galaxies in their raw, formative years. This means the night sky is not a static painting, but a vast, layered historical archive. The brighter, younger stars show us recent cosmic history, while the faint, deep-field galaxies reveal the ancient universe. Every glance upward is a look back in time, connecting you directly to the epic saga of the cosmos. This layered view of cosmic history reveals a timeline that seems to march relentlessly forward. But what if the arrow of time is not a universal law? Some physicists propose a staggering idea that our universe is only one half of a perfect cosmic mirror. This is the theory of a CPT symmetric universe. The letters C, P, and T stand for three fundamental symmetries in physics. C is charge, meaning you could flip every particle to its opposite antimatter counterpart. P is parity, which is like viewing the universe in a perfect mirror where left becomes right. T is time itself. Our universe is not perfectly symmetric under these operations individually, but physicists have found that the combination of all three, a simultaneous flip of charge, parity, and time, seems to be a fundamental symmetry of nature. The radical proposal is that the Big Bang respected this perfect CPT symmetry. It did not create one universe, but two. The event spawned our universe and a mirror image anti-universe. In this twin cosmos, everything is flipped. Particles are antiparticles, left is right, and crucially, time flows backwards from our perspective. From the viewpoint of that anti-universe, we are the ones living in reverse. This is not about going back in time within our own universe. It is about an entirely separate cosmic realm where their past is our future and their future is our past. In such a model, the Big Bang becomes a point of perfect symmetry, a cosmic pivot from which two timelines flow in opposite directions. This idea elegantly solves several profound puzzles. For instance, it could explain why there is so little antimatter in our universe. The missing antimatter is simply all contained in the other half of the cosmos, in that mirror reality. Our universe is made of matter, and the anti-universe is made of antimatter, and the two are kept separate by the flow of time. This theory transforms our understanding of time's arrow. We perceive time as moving forward because we are caught in the flow of our particular cosmic branch. But from a God's eye view outside both universes, the entire system is static and symmetric, a frozen block where past and future eternally coexist. The flow of time we feel so intrinsically may be nothing more than a local perspective, a side effect of our place in a grander cosmic duality that we can never directly see. The idea of a mirrored universe flowing backwards in time suggests a cosmos of perfect balance, but our own reality is filled with objects of such extreme imbalance they defy common sense. Among the most bizarre relics of a star's death is the neutron star. When a massive star explodes in a supernova, its core collapses under its own immense gravity. The force is so unimaginably powerful that it overwhelms the very structure of the atom itself. The electrons orbiting the nucleus are literally crushed into the protons, fusing together to form a solid, city-sized ball of almost pure neutrons. The result is the densest form of matter we know of, short of a black hole. To grasp this density, consider a single teaspoon of neutron star material. That tiny scoop, the kind you would use to stir your coffee, would not weigh a few grams. It would weigh billions of tons here on Earth. That is the mass of a mountain, compressed into a volume smaller than a marble. It is the equivalent of taking every single human being on the planet and crushing all of our combined mass into the space of a single sugar cube. This is not just heavy, it is a state of matter so extreme that the very rules of chemistry and atomic physics cease to apply. There are no more atoms, no empty space, just a relentless, seamless ocean of subatomic particles packed shoulder to shoulder. This incredible density gives neutron stars a gravitational pull so fierce that if you were to drop a marshmallow onto its surface from just a meter above, it would impact with the energy of a nuclear bomb. The surface is a perfect, flawless sphere of solid atomic nuclei, harder than any diamond, and if there were any mountains, they could be no taller than a few millimeters, instantly flattened by the overwhelming gravity. We can detect these cosmic zombies because many of them spin at phenomenal speeds, blasting out beams of radiation from their magnetic poles like a celestial lighthouse. As they rotate, these beams sweep across space, and from our vantage point, they appear to pulse with metronomic regularity. We call them pulsars, and their steady, precise ticking allows astronomers to use them as the universe's most accurate clocks. Their rhythmic flashes are testament to the violent, dense, and utterly alien objects they truly are. Those pulsars tick with a regularity we take for universal law, a steady rhythm that seems woven into the fabric of reality itself. We assume that the fundamental rules of the game, the constants of nature, are unwavering and identical everywhere. The speed of light, the strength of gravity, the charge of an electron, these are the fixed pillars upon which our entire understanding of physics is built. But what if those pillars are not as solid as we think? What if the laws of physics themselves are not constant across the vast expanses of space and time? Astronomers have been investigating this very possibility by studying the light from some of the most luminous objects in the universe, quasars. As this ancient light travels for billions of years to reach us, it passes through interstellar clouds of gas. These clouds absorb specific wavelengths of light, creating a unique fingerprint in the quasar spectrum. This fingerprint is dictated by a number known as the fine structure constant. This constant is a crucial combination of other fundamental values, including the speed of light and the charge of the electron. It governs the strength of the electromagnetic force, which controls how atoms hold together. By analyzing these ancient fingerprints, scientists have found something unsettling. The data suggests that in certain directions of the sky, billions of years ago, the fine structure constant was minutely different from its value today on Earth. In one part of the cosmos, it might have been slightly weaker, in another, slightly stronger. The change is incredibly tiny, but its implications are seismic. It means that the force which governs the structure of every atom, every molecule, and every chemical reaction might not be a true constant. It could be a variable, slowly changing over cosmic time or differing from one galactic supercluster to another. If this is true, it shatters the principle of the uniformity of nature. The universe would not be a single, coherent entity governed by one set of rules. Instead, it would be a patchwork of different domains, each with its own slight variations in the laws of physics. In such a cosmos, the conditions that made our life possible would not be a universal given. There could be vast regions of space where the electromagnetic force is too weak for atoms to form stable molecules, preventing chemistry and life as we know it from ever arising. Other regions might have forces so strong that stars burn out in a cosmic blink. Our corner of the universe would be just one possible configuration, a lucky island of stability in a sea of physical chaos. This challenges our most profound assumptions about reality, suggesting that the very rules we rely on to understand the cosmos might themselves be mere local ordinances. While we ponder whether the laws of physics themselves might be a local phenomenon, we can find comfort in a discovery that is both universal and strangely familiar. Drifting in the heart of our own galaxy is a cosmic brewery of unimaginable proportions. Known as Sagittarius B2, this vast molecular cloud contains enough ethyl alcohol, the very same kind found in your favorite drink, to fill thousands of Earth's oceans. This is not a trace amount, it is an immense reservoir of booze, a cloud of vapor, and dust so large it could easily engulf our entire solar system. But this cosmic bar is not just serving ethanol. Within its frigid depths, astronomers have identified a rich cocktail of complex organic molecules, from simple ones like carbon monoxide to more intriguing compounds like vinyl alcohol and even aminoacetonitrile, a direct precursor to glycine, one of the fundamental amino acids that form proteins in all known life. The existence of this cloud is not a quirky anomaly, it is a profound statement about the chemistry of the cosmos. the basic building blocks of life are not rare or special. They are forged in the nuclear furnaces of ancient stars and scattered across the galaxy in stellar explosions, seeding interstellar clouds with the essential ingredients for chemistry. This means that the raw materials for life, the sugars, the acids, the alcohols, are a natural and abundant byproduct of cosmic evolution. They are woven into the fabric of the galaxy itself, waiting in the frozen darkness of space for the right conditions to spark them into something more. The universe, it seems, is pre-stocked with the potential for life on an almost incomprehensible scale. That cosmic bar, brimming with the ingredients for life, exists within a galaxy governed by the same gravitational rules that orchestrate a bizarre dance much closer to home. The planet Mercury performs a celestial rhythm so strange it defies all our Earth-bound intuition. A single year on Mercury, one full trip around the Sun, is completed in just 88 Earth days. But the planet spins on its axis so slowly that a single day, one full rotation, takes 59 Earth days. This already seems odd, but the true strangeness is revealed when you consider a solar day, the time from one sunrise to the next. On Mercury, this familiar cycle stretches to a staggering 176 Earth days. This means a single day on Mercury is twice as long as its entire year. The Sun would crawl across the sky, taking what feels like an eternity to complete a journey we see in just 12 hours. Imagine celebrating 2 New Year's days before you've even experienced a single sunrise to sunset. The reason for this lies in a gravitational tug-of-war called a spin-orbit resonance. Mercury is locked in a precise rhythm with the Sun, rotating exactly 3 times for every 2 orbits it completes. This, combined with its wildly elliptical, egg-shaped path around the Sun, creates the extraordinary effect. As Mercury approaches the Sun on its oval orbit, its speed increases dramatically, pulled by the intense gravity. For a person standing on its surface, this would create an unbelievable spectacle. The Sun would appear to slow down in the sky, stop, and then actually reverse its course for a time before slowly moving forward again. A single daytime period from one noon to the next becomes a marathon event lasting nearly half an Earth year. This cosmic waltz is a perfect demonstration of how gravity does not just pull objects together. It choreographs their every move, creating a solar system far more dynamic and peculiar than a simple set of orbiting clocks. That same gravitational choreography that dictates Mercury's strange day is also pulling our own moon into a slow, cosmic retreat. The moon is drifting away from us at a rate of nearly 4 centimeters every single year. This slow-motion departure is a direct result of the tidal dance between our world and its companion. The moon's gravity does not just pull on our oceans, creating the tides, it also creates a much smaller, yet crucial, tidal bulge in the solid body of the Earth itself. Our planet rotates faster than the moon orbits us, so this rocky bulge is constantly being dragged just ahead of the moon's position. This forward-leaning mass exerts its own gravitational pull on the moon, giving it a tiny, constant tug forward in its orbit. Energy is conserved, so this boost to the moon's orbital energy comes at a direct cost to Earth's rotational energy. We are literally spinning ourselves down to speed the moon up. Think of it as a cosmic friction brake, gradually transferring the spin of the Earth into a higher, slower orbit for the moon. The ultimate effect is that our planet's rotation is imperceptibly slowing, making our days longer by a tiny fraction of a second each century. Over millions of years, these increments add up. In the distant past, a day on Earth was only a few hours long, and the moon loomed much larger and closer in the sky. Project this process billions of years into the future, and a profound change awaits. The moon will have retreated so far that its apparent size in our sky will no longer be large enough to completely cover the Sun. The breathtaking spectacle of a total solar eclipse where day turns to night and the Sun's corona blazes around a black disk will become impossible. Future inhabitants of Earth will only ever witness partial or annular eclipses, a brilliant ring of fire, but never again the total, awe-inspiring darkness that we are privileged to see. This slow drift is a reminder that even the most permanent features of our sky are part of a dynamic and ever-changing cosmic system. Far beyond our solar system, a world exists where the very ground beneath your feet would be a fortune beyond imagining. Scientists have identified an exoplanet known as 55 Cancri e, a super-Earth whose composition is so rich in carbon that its interior is likely a colossal diamond. This planet orbits its star so closely that a full year passes in less than 18 hours, and surface temperatures soar high enough to melt iron. Under such hellish conditions of immense heat and crushing pressure, the carbon that forms the bulk of the planet is forced into a crystalline structure, creating a layer of diamond that could be hundreds of miles thick. We are not talking about a few scattered gems, but a world that is essentially one gigantic planet-sized jewel. The discovery of such a world forces us to reconsider what is possible in planetary formation. We are accustomed to rocky, silicate-based planets like Earth, built from common elements like oxygen and silicon. But 55 Cancri e is a carbon world, a type of planet that forms in a system with a high ratio of carbon to oxygen. In such an environment, carbon compounds like carbides and graphite dominate, and given the right pressure, that graphite transforms into the hardest natural substance known. How can we possibly know the composition of a world so distant we cannot even directly image it? Astronomers use the subtle wobble of its host star and the periodic dimming of its light as the planet transits or passes in front of it. By analyzing the starlight that filters through the planet's hypothetical atmosphere, they can detect the chemical fingerprints of elements, revealing an atmosphere likely rich in carbon monoxide and hydrogen cyanide, but startlingly devoid of water vapor. This diamond planet is not a solitary oddity. Its existence implies that our galaxy is filled with a staggering variety of worlds, from water worlds to lava planets, and now to glittering carbon kingdoms. It challenges our Earth-centric view of what makes a planet, suggesting that the universe is a place of far stranger and more wondrous possibilities than we ever dreamed. Even the void between stars is a place of ceaseless, frantic activity. We call space a vacuum, a word that conjures images of absolute nothingness, but this is a profound illusion. At the tiniest scales, the realm of quantum mechanics, the vacuum of space is not empty at all. It is a seething, bubbling sea of energy constantly in motion. According to quantum field theory, what we perceive as empty space is actually a field of fluctuating energy. These fluctuations are so intense that they momentarily borrow energy from the vacuum itself to spontaneously create pairs of particles and antiparticles. A single electron and its antimatter twin, a positron, can simply wink into existence from nothing, but there is a catch. The universe demands its energy back almost instantly. These virtual particles, as they are called, are forced to annihilate each other and vanish back into the quantum foam in a time span so short it is almost incomprehensible. This endless, frantic dance of creation and destruction happens everywhere all the time, even in the space between your fingers as you read this. The vacuum is alive with these fleeting ghosts. This background hum of activity has a name: zero-point energy, the lowest possible energy that a quantum system can possess, and it is not zero. Empty space, therefore, possesses a fundamental, irreducible energy. But how can we possibly know this is real and not just a mathematical quirk? We have experimental proof in a phenomenon called the Casimir effect. Imagine two perfectly smooth, uncharged metal plates placed incredibly close together in a vacuum, separated by a gap smaller than the width of a human hair. In the empty space outside the plates, virtual particles of all wavelengths can spontaneously appear. But in the narrow gap between the plates, only particles with specific wavelengths that fit perfectly between them can pop into existence. This creates a pressure imbalance, with more virtual particles pushing from the outside than from the inside. The two plates are forced together. This is not a theory, it is a measured force. In a laboratory, these plates do indeed move, pulled by the sheer pressure of nothingness itself. The vacuum is not a passive stage upon which the universe plays out. It is an active participant, a dynamic fabric whose hidden energy shapes the very reality we perceive. This frantic quantum foam, a seething sea of virtual particles, exists even within the very space you occupy. And in that space, the flow of time itself is not uniform from your head to your toes. The same principle that makes a satellite's clock run faster than one on the ground applies to your own body, right here, right now. Because of gravity's relentless grip, time passes infinitesimally faster for your head than it does for your feet. The difference is almost laughably small, but it is profoundly real. Your feet are closer to the Earth's center of mass, so they are deeper within our planet's gravitational well. Just as time ran faster for the GPS satellites in the weaker gravity high above Earth, time runs slightly faster for the part of you that is farther from the source of gravity. For a person who is 2 meters tall, the time difference between their head and their feet amounts to a few 10,000ths of a second over an entire human lifetime. You will never feel this, of course. Your consciousness seamlessly blends these microscopic differences into a single, unified experience of the present moment. Yet, with instruments of sufficient precision, we can measure this effect. Atomic clocks placed on shelves just a few feet apart in height will slowly but surely drift out of sync, confirming the prediction with stunning accuracy. This is not a theoretical curiosity. It is a direct, tangible confirmation that gravity is not merely a force pulling things together. Gravity is the curvature of spacetime itself. The Earth's mass creates a dimple in the cosmic fabric, and the closer you are to the center of that dimple, the more stretched time becomes, causing its flow to slow. Your entire life is a continuous journey through these subtle gradients of time, a silent, invisible proof that the universe operates according to rules far stranger and more wonderful than our everyday senses could ever perceive. This silent, invisible proof of time's fluidity exists within a cosmos that is itself stretching at an ever-increasing rate. For decades, astronomers assumed the mutual gravitational pull of all the galaxies would act as a cosmic brake, gradually slowing the universe's expansion. The great question was whether there was enough matter for gravity to eventually halt the expansion entirely, leading to a big crunch, or if the universe would just coast onward forever. The answer, discovered by two independent teams in the late 1990s, was so shocking it earned them the Nobel Prize. They were not measuring a slowdown. They were witnessing a cosmic acceleration. The universe's expansion is speeding up. To make this discovery, the teams used distant stellar explosions called Type 1, a supernova, as cosmic mile markers. These supernovae have a known intrinsic brightness, so by measuring how dim they appear from Earth, astronomers can calculate their precise distance. They can also measure how much the light from these explosions has been stretched or red-shifted by the expansion of space. The shocking result was that the most distant supernova, whose light had been traveling for billions of years, were significantly fainter than expected. This meant they were farther away than anyone had predicted. The only possible explanation was that the space between galaxies had not been expanding at a steady rate. In the past, the expansion was slower. Billions of years ago, gravity was winning the tug of war, but then something changed. Around 5 billion years ago, an unknown repulsive force began to dominate, pushing galaxies apart with ever-increasing vigor. This mysterious something was dubbed dark energy, and it is now calculated to make up about 68% of the entire energy content of the cosmos. We do not know what it is, only what it does. It behaves like an anti-gravity force woven into the very fabric of empty space itself, causing the cosmos to blow itself apart. The ultimate fate implied by this discovery is a lonely and cold one, often called the Big Freeze or heat death. As the acceleration continues unchecked, distant galaxies will eventually be pushed beyond our cosmic horizon. Their light, stretched to longer and longer wavelengths, will fade from view entirely. The observable universe will shrink to include only our local group of gravitationally bound galaxies, adrift in an immense and growing void. Over trillions of years, stars will burn out and new ones will cease to form. The universe will become a frigid, expanding graveyard of dead stars and black holes, drifting forever into an irreversible state of dark, silent isolation. The chilling prospect of a dark, lonely cosmos is not the only possibility. Our entire universe, with its hundreds of billions of galaxies, might be just a single bubble in a boundless cosmic sea. The multiverse theory suggests that what we call the universe is merely one fragment of a far vaster reality, an infinite collection of parallel worlds. One compelling version of this idea comes from cosmic inflation. This theory posits that immediately after the Big Bang, space underwent a period of hyper-fast, exponential expansion. But what if this inflation never truly stopped? What if it continues eternally, with new regions of space constantly ballooning into full-fledged universes? In this eternal inflation scenario, our cosmos is one bubble among countless others, each nucleating out of the stretching fabric of spacetime like a bubble in a pot of boiling water. Each of these bubble universes could have its own unique properties, its own random assortment of physical constants and fundamental forces, a product of how its local inflation field settled down. In some, gravity might be immensely stronger, creating universes that collapse instantly. In others, the electromagnetic force might be too weak for atoms to ever form. Our universe, with its just right values for life, would be one rare, habitable island in an infinite ocean of mostly sterile realities. A different kind of multiverse emerges from the bizarre rules of quantum mechanics. The many worlds interpretation proposed by Hugh Everett offers a radical solution to the famous Schrödinger's cat paradox. In the standard view, a quantum particle exists in a blurry superposition of states until it is observed, at which point it randomly picks one definite state. Everett said there is no randomness and no collapse. Instead, every possible outcome of every quantum event actually occurs. At the moment of observation, the universe literally branches into multiple copies. In one branch, the cat is alive. In another, equally real branch, the cat is dead. Every time a particle could go left or right, every quantum decision made everywhere, from radioactive decay to the firing of a neuron in your brain, the cosmos splits. This means a version of you exists who made every different choice you ever considered, living out the infinite consequences of every possible life path. These are not mere philosophical speculations. They are legitimate, if currently unverifiable, extensions of our most successful scientific theories. Inflationary cosmology and quantum mechanics both point toward a reality of staggering plurality. Our entire cosmic history, from the first star to your existence at this very moment, might be just one page in an infinite library, where every story that can be written is written, and every possible version of reality is playing out somewhere. Venus presents a cosmic riddle where the basic definitions of a day and a year are turned upside down. A single year on Venus, one full journey around the Sun, is completed in 225 Earth days. Yet the planet spins on its axis with such agonizing slowness that it takes 243 Earth days to complete a single rotation. This means a day on Venus is actually longer than its entire year. If you could stand on its scorching surface, you would celebrate your next birthday before you ever saw the Sun complete one full cycle in the sky. But the strangeness does not stop there. Venus also spins in the wrong direction. From a vantage point high above the Sun's north pole, you would see most planets, including Earth, rotating counterclockwise. Venus, however, spins clockwise. This is known as retrograde rotation. On Venus, the Sun would rise in the west and set in the east, a complete reversal of our own experience. So what colossal event could have caused a whole planet to flip upside down? The leading theory points to a catastrophic impact in the deep past. A primordial collision with another large planetary body could have delivered such a tremendous blow that it literally stopped Venus's original spin and sent it rotating backwards. Another possibility involves complex gravitational interactions with the Sun and a thick, soupy atmosphere over billions of years, creating tidal forces that gradually slowed and then reversed its spin. This bizarre temporal and directional reversal makes Venus a world of profound contradictions, a place where time itself seems to follow a different set of rules, forever challenging our Earth-centric expectations of how a planet should behave. That same photon, born in the cosmic dawn, experiences a reality utterly alien to our own. While we measure its journey across the universe in billions of years for the photon itself, the trip is over in the very same instant it begins. Time, from its perspective, does not pass at all. This is the ultimate consequence of Einstein's time dilation taken to its logical extreme. The closer any object gets to the speed of light, the more its internal clock slows down relative to a stationary observer. A photon, by its very nature, travels at this ultimate speed. For it, the clock does not just slow, it stops completely. The mathematical equations of relativity show that at the speed of light, time dilation becomes infinite. The duration of any trip, whether it is from a distant quasar or the screen in front of you, contracts to zero. This means light is fundamentally ageless. A photon that has been traveling since the first moments of the universe is no older now than it was at the moment of its creation. It has no memory of its journey, no experience of distance. The entire cosmos, from its point of view, is a single, timeless point. It is emitted and absorbed in the same non-existent moment, connecting two events across the vastness of space with a bridge of pure instantaneity. This forces us to confront a profound truth. The universe is filled with ancient messengers that carry the history of the cosmos, yet each one exists in a state of perpetual, frozen youth. Our own solar system may harbor a final, undiscovered giant. Far beyond the orbit of Neptune, in the frigid, sunless depths of space, a handful of small, icy bodies are behaving strangely. Their orbits are clustered together, tilted in a way that suggests they are all being shepherded by the gentle but persistent gravitational tug of something massive. This is the primary evidence for a hypothetical Planet 9, a world that could be 10 times the mass of Earth lurking in the outer darkness. Astronomers are not seeing this planet directly, but they are seeing its ghostly signature written in the paths of these distant Kuiper belt objects. It is as if we are watching a school of fish all suddenly change direction and inferring the presence of an unseen shark moving deep below. The hypothetical orbit of this world is almost incomprehensibly vast. While Pluto takes 248 years to orbit the Sun, Planet 9 would complete a single, lazy loop only once every 10 to 20,000 years. At its most distant, it would be over 1,000 times farther from the Sun than Earth is. If it exists, it would be a super-Earth or a mini-Neptune, a type of planet that is common around other stars but conspicuously absent from our own inner solar system. Finding this frozen behemoth would be a monumental achievement, fundamentally rewriting our solar system's family portrait. It would confirm that our cosmic neighborhood has always had this distant, silent guardian, its immense gravity subtly shaping the architecture of our planetary system from the shadows for billions of years. The hunt is on, with telescopes scanning the predicted swath of sky, trying to catch a glimpse of this celestial phantom whose presence we can only feel through its gentle pull on the smallest members of our Sun's kingdom. That unseen Planet 9, if it exists, would be just one more speck orbiting the true master of our cosmic neighborhood. all the planets, moons, and asteroids combined are merely cosmic dust compared to the Sun. Our star alone contains 99.86% of the entire solar system's mass. To grasp this staggering imbalance, picture a cosmic scale. Place the Sun on one side, a colossal ball of incandescent plasma. On the other side, you would need to pile everything else. That includes the giant Jupiter, which itself is more massive than all the other planets put together. It includes the ringed beauty of Saturn, the ice giants Uranus and Neptune, and our own rocky world, Earth. You would add every single moon from our own silver companion to the dozens orbiting Jupiter and Saturn. You would sweep in the entire asteroid belt between Mars and Jupiter, and the countless comets and icy bodies of the distant Kuiper belt. When you are finished, that immense pile of everything else in our solar system would still only account for a pitiful 0.14% of the total weight. The Sun is the gravitational anchor of our entire system. Its immense pull is the reason every planet, including a potential Planet 9, is locked in an eternal dance around it. This is not a partnership of equals. The Sun's gravity dictates the rhythm of every orbit, the length of every year, and the very stability that has allowed our world to exist for billions of years. We are all just minor attendants to a stellar sovereign, living in the thin, scattered leftovers from its formation. Our Sun is a colossal, churning ball of incandescent plasma, a continuous thermonuclear explosion. Yet if you were floating beside it in the void, you would experience a deafening, absolute silence. The vacuum of space is the quietest place imaginable because sound, as we know it, cannot exist there. Here on Earth, sound travels as a pressure wave, a vibration that needs a medium to move through, whether it is air, water, or the ground. In the emptiness between stars and planets, there is no such medium, no atoms packed closely enough to bump into one another and carry the vibration forward. All those epic cinematic battles with roaring starship engines and exploding planets are a dramatic lie. In reality, a supernova, the most violent stellar explosion possible, would rip through a solar system in utter, complete silence. This does not mean space is devoid of waves or vibrations. Stars and planets generate immense magnetic fields and powerful plasma waves, but these are electromagnetic vibrations, not pressure waves, and our ears are not built to hear them. If we could somehow translate these signals into sound within a spaceship, we would hear an eerie symphony of crackles, pops, and whistles, the ghostly choir of the cosmos. But outside the hull, in the true environment of space, the silence is profound and unbroken. It is a constant reminder that the universe was not built for our senses, and that its most fundamental nature is often hidden from our direct experience. That profound silence of space is broken not by sound, but by an unseen and relentless pull. Our entire galaxy, the Milky Way, is not simply drifting through the cosmos. It is racing towards a specific point in the sky, a mysterious gravitational anchor known as the Great Attractor. Located hundreds of millions of light years away in the direction of the Centaurus and Hydra constellations, this colossal region of space exerts a pull so immense that our galaxy, along with our entire local group of galaxies and even vast superclusters beyond, is flowing towards it in a river of cosmic motion. We are caught in a current we cannot see, moving at over 1,000,000 miles per hour towards a destination we do not fully understand. The very existence of the Great Attractor was first inferred not by what we could see, but by what we measured. By observing the subtle motions of thousands of galaxies, astronomers noticed a consistent deviation from the overall expansion of the universe. A vast swath of the cosmos, including us, was not just receding from the Big Bang, it was also being tugged sideways towards this single, powerful gravitational focal point. It is as if we are all leaves floating on a wide, expanding river, but a powerful whirlpool is pulling us inexorably towards its center. The true identity of this cosmic whirlpool, however, is frustratingly difficult to pin down. It lies directly behind the plane of our own Milky Way, in a region astronomers call the zone of avoidance. This is the thick, dusty, star-filled central disk of our galaxy, which acts like a cosmic fog bank, completely obscuring our optical view of the universe beyond. Trying to see the Great Attractor is like trying to see a distant mountain range through a dense, permanent thunderstorm. We know something massive is there, but our primary eyes, optical telescopes, are blinded. To pierce this veil, scientists have turned to other wavelengths of light, like infrared and radio waves, which can penetrate the interstellar dust. These observations have revealed that the Great Attractor is not a single, unimaginably dense object like a supermassive black hole. Instead, it appears to be the heart of a colossal supercluster of galaxies, a gravitational nexus known as the Laniakea supercluster. Laniakea, a Hawaiian word meaning immense heaven, is the cosmic continent to which our Milky Way belongs. The Great Attractor is its most massive and dominant gravitational valley, the central point towards which everything in our local supercluster flows. Yet, even this colossal structure may not be the final answer. The pull we feel might be caused by something even larger and more distant lying behind it, a structure so immense it is tugging on the Great Attractor itself. This reveals a universe of nested gravitational influences where we are drawn to a local center, which is itself being pulled towards a grander one in an endless cosmic chain of motion. We are not merely expanding, we are on a journey pulled through the silent darkness towards a mysterious, unseen heart. Our silent journey toward the Great Attractor is a voyage across a cosmic ocean, but what if the universe provided secret passages to skip the trip entirely? The final mind-blowing fact brings us to one of the most captivating ideas in all of physics, the wormhole. Also known as an Einstein-Rosen bridge, a wormhole is a theoretical tunnel, a shortcut through the folded fabric of spacetime itself. Imagine our universe is the surface of a vast sheet of paper. A wormhole would be like a pencil stabbing through the paper, creating a tunnel connecting 2 points that would otherwise be a long journey across the sheet. These bridges could, in theory, connect not only distant parts of our universe but potentially different points in time or even entirely separate universes in the multiverse. The mathematics of general relativity allows for such structures, but turning the equations into a stable, traversable gateway is another matter entirely. The central problem is that these hypothetical tunnels are incredibly unstable. The moment one forms, it would likely pinch off and collapse into a singularity faster than the speed of light, crushing anything inside. To keep a wormhole open, to prop its throat wide enough for matter or a ship to pass through, you would need a truly bizarre substance. Physicists call it exotic matter. This is not just matter that is weird or unknown. Exotic matter would have to possess negative energy density, effectively generating a kind of anti-gravity that pushes the walls of the wormhole apart, preventing its catastrophic collapse. While we can create tiny amounts of negative energy in lab experiments with quantum effects like the Casimir effect, the amount needed to stabilize a wormhole of useful size is astronomical and far beyond our capabilities. So, could we ever use one for travel? The dream of stepping through a portal to another galaxy or another time remains firmly in the realm of science fiction for now. Yet, the mere possibility that the geometry of reality might include such incredible shortcuts forces us to confront a universe that is not just vast, but intricately connected in ways we are only beginning to mathematically imagine. The cosmos may be filled with hidden doors, waiting for a future civilization with the knowledge to find the key. We have traveled from the flexible nature of time in our own pockets to the silent, ghostly pull of the Great Attractor, uncovering a cosmos that defies common sense at every turn. These 25 glimpses reveal a universe where time is a personal rhythm, where the ground beneath your feet ages slower than your head, and where the vast majority of reality is built from invisible dark matter and propelled by a mysterious dark energy. We have encountered worlds of solid diamond, witnessed spacetime itself ripple, and pondered the existence of a mirrored universe where time flows backwards. This journey is a powerful reminder that our everyday experience is a tiny, narrow window into a reality of staggering scale and profound strangeness. The universe is not merely a collection of distant lights. It is a dynamic, evolving, and deeply mysterious entity, filled with more wonder than we could ever fully comprehend. So the next time you find yourself under a clear night sky, take a moment to really look up. Remember that you are not just seeing points of light, but ancient history, cosmic collisions, and the invisible scaffolding of existence itself. Let that feeling of awe sink in. We would love to hear which of these facts reshaped your view of the cosmos the most, so share your favorite in the comments below. If your curiosity is sparked, be sure to subscribe and join us as we continue to explore the deepest mysteries of space and time.